This is part 3 of the video lecture for Math 181 for Monday, April 27th. And we're talking about using integrals to calculate the volume of solid objects. In this example, we want to calculate the volume of a solid obtained by rotating the curve y equals x squared about the y-axis. Okay, not about the x-axis anymore, about the y-axis from y equals 0 to y equals 4. So again, the first step in this problem is to make a graph. I'm going to do that here. So here's our graph. Here's a simple graph. This is just a parabola, right? So this looks like this. Like that. That's a parabola. Okay. But in this case, we're going to rotate this curve about the y-axis, not the x-axis. So that will create a different shape. It'll create a certain shape, right? And we could divide this up into slabs, right? And so we're going to imagine we're going to rotate this around the y-axis, okay? And what will this look like? Well, let's try to draw an accurate depiction of it. This is our x-axis. This is the y-axis here. We have our curve. Looks like a parabola. Then it's going to rotate around the other side of the axis too. And then it's going to look like this, right? And we're going up to the point y equals 4. For our solid. So when we rotate this curve around the y-axis, we're going to get a solid that has this shape. It's kind of a parabola bowl-shaped solid, but it's filled in the middle. And we want to calculate the volume of this object. Okay, well, let's look at the slab here. We've got a slab like this, okay, that goes back around like this. And it has some thickness, right? It has some thickness like this. It goes back around like this. Okay, that's our slab we're interested in. So it looks something like this. See if I can draw this accurately. This is our disc shape here. Now, what is the thickness of this disc? Okay, in this case, because we're rotating around the y-axis, the thickness of our disc is dy. Okay, and what is the radius of this disc? The radius is simply this distance right here. Well, what is this distance? This distance is x, right? That distance is x. It's not y because now we're rotating around the y-axis. This distance is x. So our radius is x. And now the area of this, and our area now is a function of y, not x, because, again, everything changed because we're rotating around the y-axis. So the area of each disk is going to be a function of where you are along the y-axis. In fact, the area will get bigger as you go higher up along the y-axis. So the area as a function of y will be equal to pi, okay, times the radius squared. So pi times x squared is the area of each disk. Okay, but we know from this equation, right? We know that x squared equals y, and so we can replace x squared with y. And therefore, the area of each disk as a function of y is pi times y. Okay, now we can do our volume integral. The volume, so again, what are we doing? We're dividing this solid into a series of slabs, but in this case, they're horizontal slabs, and we're going to add up the volume of each slab to get the total volume. So the volume will be the integral, okay, of our area as a function of y, times the thickness of each slab, which is dy. In this case, we're integrating over y and not x. We're integrating up like this. And therefore, our limits are in terms of y. We're integrating from 0 to 4. So we take the integral from 0 to 4 of a of y dy. Okay. And that would be equal to, let's plug in here, so we get the integral from 0 to 4 of pi y dy. Okay, now we can pull out this pi, we can perform this integral. It doesn't matter if it's over y, we can still do the integral, use the same technique we've used. This is the integral from 0 to 4 of y dy. And if you evaluate this integral, it becomes pi y squared over 2, right? Evaluated from 0 to 4. So now we're going to plug in here, we get pi over 2 times 4 squared. The 0 term goes away. 4 squared is 16, this equals 8 pi, right? That's 16 divided by 2 is 8. So the answer here is the volume of this solid is 8 pi. So the moral here is we can also rotate curves around the y-axis as well as the x-axis. Okay, I want to do one more example with you guys, and that will conclude this video lecture. Now I realize this is hard stuff. Where integrals are hard, and we're applying integrals to three-dimensional shapes. This is hard. One thing that makes it hard is trying to imagine a three-dimensional shape. It's easier to imagine a two-dimensional shape. Okay, in example 4, we want to obtain the volume. So we want to calculate the volume of the solid obtained. The volume of the solid obtained by rotating the region enclosed by the curves y equals square root of x and y equals x squared about the x-axis. Okay, that's a mouthful. What's going on here? We want to calculate the volume of the solid obtained by rotating the region enclosed by the curves y equals square root of x and y equals x squared about the x-axis. Okay, so what the heck is going on here? Well, let's draw a graph of this first. Okay, y and x. And I'm going to graph these two curves. Y equals square root of x looks like this. It kind of tails off. Y equals x squared is a parabola that grows like this. Okay, so these are the two curves I have. And we did this problem before. We calculated the area enclosed by these two curves. And so I get an area that's enclosed right here. Okay, and what we're going to do in this case now, though, is we're going to take this kind of fish-shaped area, enclosed region, and we're going to rotate it around the x-axis. That's pretty weird, right? We're going to rotate this region about the x-axis. Okay, and that's going to lead to a three-dimensional shape. Let's see if we can draw that three-dimensional shape. And this is going to produce a three-dimensional shape that looks something like this. Like this, and then it's going to get closed off right here, like this. Okay, but then if we draw a cross-section, let's consider a cross-sectional slab of this shape. And so this is going to look like this. The thing is, this shape will be... Ooh, I'm not drawing this correctly. This shape will be a washer shape. I didn't quite depict this correctly here. I'm just going to skip the dashed lines. That's confusing more. Now you're seeing more artistic limitations. Okay, so what happens here is we get, this is pretty rough, but we get a washer. You guys get the idea. This is a washer shape here. So our slab, our cut through this shape, this solid object, gives us a washer shape. So this is kind of a weird solid object that that has a certain kind of volume to it. It's like a bowl. It's kind of hollow inside, but the thickness of the bowl varies, gets thicker, and comes back like that. Here's our washer. Let's draw this. Let's do a cross section of this washer. This washer has a thickness dx. Okay, I'm going to draw it over here as a cross section of it. Okay, and we want to calculate the area of the washer. Okay, well, this is our inner radius Ri, and this is our outer radius R outer. Okay. How do we calculate the area of a washer? Well, the area of a washer is equal to, you can think of it like the area of the big circle minus the area of the small circle. So the area is going to be pi times R outer squared minus pi times R inner squared. And this simplifies to, we factor out the pi, we get R outer squared minus R inner squared. This is the area of a washer. Okay. And let's now apply this to this problem. In this problem, right, this curve right here is y equals square root of x. This curve right here is y equals x squared. So our outer, hopefully you guys see, the outer radius of this washer is the top curve. So our outer radius is equal to square root of x. Our inner radius is equal to the lower curve, and that's x squared. Okay, and now the area will be equal to pi times the outer radius, square root of x squared, minus the inner radius, which is x squared, squared. Okay, that's what we get. And the area, if we simplify this, square root of x squared is simply x. So this is pi x squared squared is x to the fourth. So the area of this washer for this solid object is equal to pi times x minus x to the fourth. Okay, we're not done with the problem yet, but that's our area. Now we're going to calculate the volume. The volume will be the integral, and now we need to figure out the limits. Okay, you know, what are the limits of integration? We're going to integrate from here to here, the points of intersection. If you guys remember, I think we did this problem before. That's the point of intersection. If you guys can guess the point of intersection, it's 1, 1. Okay. How do you obtain that? This is the point where these two curves are equal. We did this problem before, but basically you set square root of x equal to x squared, and you solve for x, and that comes out to x equals 1. So our limits of integration are from 0 to 1. We're going to integrate our area function, which is pi times x minus x to the fourth. Okay. Thickness dx. Now we're going to do this integral. It's equal to pi times 0 to 1 of x minus x to the fourth dx. Okay. And now if we integrate this, we get pi times the integral of x is x squared over 2. The integral of x to the fourth is x to the fifth over 5. Okay, evaluated from 0 to 1. Those are our integration limits. Okay, let's plug those in. So now if we plug these in, the 0 part of this just goes away because we have x's here. So we simply get pi times 1 half. If we plug in 1, we get 1 half minus 1/5. And now we can find a common denominator here. This is like, the common denominator is 10. This is like 5 over 10 minus 2 over 10. Okay, and this simply equals, it equals pi, 3 pi over 10. Let me circle that. So the volume, this is kind of strange, but if we have this enclosed region here, and we rotate it around the x-axis, we create this weird shape. It's kind of a hollow bowl shape, but then the thickness of the bowl is thicker here than it is here or here. And the volume of the shape is 3 pi over 10. So that's another example of using integration to calculate volumes of solid objects. I will see you guys on Monday.